Hello! Today we're going to start talking about Chapter 10, which involves energy and work and power and machines. And so today, before we talk about machines, we're going to talk about energy and work. Alright, so let's start off with work. So work is the product of the force on an object and then that object's displacement. And so product is going to be a multiplication. And so to find work, we want to take the force on the object times how far the object moved or was displaced. Hey, energy is also involved in order to do work. So energy is the ability of an object to produce a change in itself or the world around it. So when we talk about the system, is the system doing work or is the world doing work on the system? And energy, in our case, involves kinetic energy, which is the energy of motion, which we're going to abbreviate as KE. And so kinetic energy to solve is equal to 1/2 times the mass of the object times its velocity squared. And just the velocity term is squared, not the entire equation, just velocity. Oops. Well, we can relate work and energy to each other, and we have what's called the work and energy theorem. So when work is done in an object, the result is a change in kinetic energy. And so we can say that work is equal to change in kinetic energy, which anytime we have a change, it's a final minus initial. Work and energy were researched by James Prescott Joule, so units of energy and work are going to be joules, which is a capital J. Alright, well, energy can move between the external world and the system while doing work, so we can go back and forth. But work is going to be either positive or negative, depending on that transfer of energy. So work is the transfer of energy by mechanical means, and we can have two different perspectives on this. If the external world does work on the system, then work would be considered positive and the energy of the system would increase. If we had the opposite situation, where the system was doing work on the external world, then work would be negative and the energy of the system would decrease. And we'll do some examples of that. Okay, so we know that work is equal to force times displacement. Well, we can have lots of different forces since force is a vector, and it won't always occur in the same direction as the displacement. And so we need to look at when would a force be counted as doing work and when wouldn't it. If we have a perpendicular force, that is not going to contribute to work. Work equals force times displacement is only for constant forces exerted in the direction of motion. So if you have a perpendicular force, it's not going to change the speed, and the kinetic energy is going to stay constant. If kinetic energy stays constant, we know that through the work-energy theorem that change in kinetic energy is caused by work. So if the change in kinetic energy is 0, then the work done is 0. So if force and displacement are at right angles, or if the force is perpendicular to the direction of motion, then work is going to equal 0. So the only time that we can have work is if force is in the direction of motion. If the force is exerted perpendicular to the direction of motion, it won't do any work. Well, we've talked about forces in the direction of motion, forces perpendicular to the direction of motion, and now we're going to talk about forces exerted at an angle. Well, because force is a vector, we can break it up into its components. And so the direction could be either positive or negative. And so, for example, let's say that we had a wagon, and it was moving in the horizontal direction. But we're applying a force at an angle. Well, we can take that and break it up into our components of horizontal and vertical components. And if we look at the idea that force must occur in the direction of motion, since our direction of motion is horizontal, then the only component of force we can use is the horizontal component. Now, if we have this angle, then that makes it the cosine or the adjacent to the angle. And so overall, the equation is force times displacement cosine theta. But remember, like we've talked about before, all this is really due to is that usually we have this angle and things are usually moving horizontal. And so what you're really just trying to find is the component of the force that's in the same direction as the motion. So work must be in the direction of displacement. So for example, if we were pushing a car, there are a lot of other agents that exert a force besides the person pushing on the vehicle. You can have friction, which is the opposite of motion. so it would be negative and reduces the kinetic energy of the system. Because remember, positive work will increase energy, negative work will decrease energy. We also have gravity acting on the car and the ground, or what we would call the normal force, pushing up on the car. However, because gravity and the ground force are not in the direction of motion, we're not going to look at them as far as contributing to the work done. And so they cannot do any work on the vehicle, and so we're only going to look at horizontal forces since we're pushing the car in a horizontal direction. Alright, well, what about when we have forces that change? Well, in this case, we could do the area under a force displacement graph to get the work, and that would be the work done by that force. And so just like when we talked about impulse, taking the area under a force time graph, because work is force times displacement, this would be the same thing for a force that changes over time. Okay, what about work that's done by many forces? Well, we can just add those together, and so to get the total amount of work, we would just add up all the forces that were in the direction of motion. Alright, so the last part that we're going to talk about here is power. Now, so far, we've talked about work and energy, and work does not really depend on time. It depends on force and displacement. Well, power is the rate at which work is done, and anytime you have a rate, it's in a unit of time. And so power is the rate at which an external force changes the energy of a system, or work divided by time. Units for power are watts, which is a capital W, which it could also be written as joules per second, since the units for work are joules, and then our time unit is seconds. The less time it takes to do something, the more power it has. And so if we look at our units, which is a watt, watts are often very small, and so we usually measure things in kilowatts. So a kilowatt is 1,000 watts, just like a kilogram is 1,000 grams. Okay, so we know that power is work divided by time. And we know that work is force times displacement. And so we can rearrange the power equation to say that it's equal to force times displacement divided by time. Well, if we take a look at the variables that we have, we know that distance over time is equal to velocity. And so we can also rearrange our power equation, substituting velocity in for the distance over time, to get that power is equal to force times velocity. And so we have a couple different situations we can use for the power equation. If the force is 0 or the velocity is 0, then no power is being produced. A combination of a medium force and a medium speed are going to produce the largest amount of power, and this is true for machines and for humans. And so in the next section, we're going to get into machines and talking about efficiency and things like that. Alright, so let's kind of summarize what we've talked about. We talked about the work-energy theorem, where work, which equals force times displacement, equals the change in kinetic energy, which is equal to 1/2 mass times velocity squared. We know that work can be positive or negative depending on where it is applied. If the system is doing the work on the environment, it's negative, and if the environment does work on the system, it's positive. We also know that in order to have work, force must be in the direction of motion. And so if we have a force at an angle, we need to break it into components and find the component of that force that is in the direction of motion. And then finally we talked about power, which is the rate at which work is done. And so power is equal to work divided by time, or force times velocity. Alright, these are the practice problems that we're going to do in class. We're going to look at work and energy, work with force at an angle, and some power problems. And then if you would also like to get started on the individual practice, here it is along with the answers. Have a good day.